Uh, so like Adam said, I'm going to talk to you about coping with the data stream from LSST. And really, this talk is about putting everything that you've learned, not just in this session, but I also sort of went back and looked at the previous sessions that you'd gone through, session 1 and session 2. And I realized that we could integrate a lot of the stuff that you'd learned and sort of hopefully reinforce them by talking about one specific science case where you use all of these things. So before that, I guess Adam said we should have a slide up about the stuff I work on. Most of the work that I do is actually using type 1a supernovae to try to understand what the nature of dark energy is. ANTARES is in some ways an offshoot of that because I want to find a very large photometrically selected sample of type 1a supernovae that's very pure. And so I need to be able to find this with LSST, and you need some way of processing all the alerts from LSST to be able to locate that. I build models for type 1a supernovae to infer their distances. You'll hear things that masquerade as type 1a supernovae because we don't want them in our sample. I work a lot on image reduction pipelines. I did the difference imaging pipeline for Essence and Pan-STARRS along with Arm and Rest in Marcuba. And to date, that thing has processed about 900 terabytes of data. But hopefully we'll get up to like a petabyte soon. There's stuff I work on for calibration of large surveys, but I'm not going to talk about any of that here. So come by NOAO's room 118 if you need to chat with me. So the sort of stuff that you've covered so far in this data science fellowship program is stuff like time series analysis, machine learning, object-oriented programming in this session, databases again in this session from this. I did a beautiful job of introducing you guys to the profiling code today. So that link isn't active. I'll put that in after this talk. And visualization stuff. And really, they've had to effectively be siloed because there's only so much you can be introduced to at once. On the other hand, you're now 3 sessions in, and a lot of this stuff is becoming more and more familiar to you, and hopefully we can put them all together in this one project. And the context in which we'll do this, of course, is LSST. So this is an image that Beth showed a little video of earlier on, and this image terrifies me because LSST is not that far away. This thing will get done faster than you and I will be ready for it. The codes, I promise you, having worked on some of these surveys, we'll find ourselves in 2023 and still not have perfectly developed algorithms and pipelines ready to deal with the data. And the data will be overwhelming. So just to give you a sense of scale, this is what Moore's law buys you. This is my academic granddad, Bev Oak. And this is him in 1990, very proudly holding a 0.24 megapixel CCD. It was, at the time, the largest astronomical CCD in the world. Cool, eh? This is John Tondry standing in front of GPC-1 for Pan-STARRS. You can see that he's smiling despite the mask. And it is a monstrous thing. Pan-STARRS produced an absolute ton of data. And what a ton of data buys you, if you sort of compare how that evolution's happened from the 1990s to now, is a lot more objects. So this is Saul Perlmutter's Hubble diagram from 1999. This is a thing that won the Nobel Prize, and there's just not that many objects. And that's from my thesis. There's way more objects on that thing. And really, this is going from a 16 megapixel detector to a 64 megapixel detector on our camera, and similar amounts on other cameras. And LSST is just way bigger than all of these things. So that's the LSST detector with a person next to it for scale. And all of our transient searches so far have really relied on looking at the data from these telescopes and these giant cameras with our eyeballs. I'm going to give you an actual idea of how that worked. Okay? So when I was a young grad student, I got stuck on this project called Pan-STARRS. And Pan-STARRS produced a lot of alerts. Every one of these stupid links is an alert. Every one of those alerts is a light curve. Some poor chump, me, looked through these damn things and decided, some of these need to be followed up with a spectrograph. And so we clicked on some of these things and went and got spectra of them. Sometimes they were type 1As, which I wanted to find. Sometimes they were weird SME with high velocities. And all of this was done by hand. Some poor human being actually had to maintain these things. And we had a nice interface to do all of it. But really, this was a very visual process, okay? If you wanted associated data, well, we gave you some links, and so you could go click on SDSS to get what the object was, and hopefully you had a piece of pen and paper to write down what the thing was and do your science. That can't possibly work with LSST, right? I can't possibly work with LSST because the data rate is just way too high. So what you essentially get is a flood of these alerts all the time, and you're going to dominate. So it's a 10 million alerts a night, and the problem isn't just the amount of it, it's the rate of it, okay? Every 37 seconds, we're going to get an image from LSST. And that image is going to have between 10,000 and 100,000, or sorry, 1,000 and 10,000 alerts that will be mostly junk. And in that junk, there will be some real objects that you actually want to find. And we have to do all of that processing in 37 seconds. And if we fall behind, we just drop an image because we can't catch up. So that's problem number one with LSST. Problem number two is actually possibly more challenging. And pop quiz, what is synoptic? What does it mean?
All sky.
All sky? Any other ideas?
Does it mean that you basically do data analysis on the fly?
No. So this is great, right? You guys are 3 sessions into the LSST-C Data Science Fellowship Challenge, and you have no idea what synoptic means, which is basically the same state that everybody else is in, which is good, because synoptic is more overarching view of the entire subject. It gives you a synopsis, okay? What that actually translates to is everybody is going to disagree with each other as to what the heck they actually want. And so they're all going to have contradictory science goals and are going to try to push these projects in very different ways. And so we have to somehow play a mediating role in all of this as well and keep everybody, well, we can't maximize happiness, so we'll try to minimize unhappiness instead. So the sort of things that we think the community will want from LSST are things that essentially need immediate follow-up. You want to have a telescope pointing at it within an hour if you can, possibly even faster than that. And some of those things, we genuinely have no idea what they are. We've never seen them before. Some of them are just very, very rare. Some things will need rapid characterization and detailed follow-up because they change at really short time scales. Some things we predicted we've never seen before. I want, for example, large pure samples of photometrically selected things like type 1a supernovae. Things like variable stars, of course, also fall into that because they can be studied in leisure. There's also objects that are just behaving weird but are otherwise really normal, potentially. And so if you want to have specific examples of those sort of things, strongly lensed supernovae, for example, would be really, really cool. They're very, very rare, though. Microlensing events, for example, Rachel Street, who works for LCO, Las Cumbres, really wants us to build a filter to go find microlensing, to find planet signatures. Everybody wants to find the gravitational wave counterpart, the EM counterpart of the gravitational wave source. I want the supernovae, some people like variable stars. You're going to hear from Luciane about Tabby star tomorrow. There's no single feature or ML algorithm that will make all of this work, okay? Let's just forget about it. It's not going to, there's no single optimal solution to this problem. So that's where we come in. ANTARES is a horrible acronym, which I won't explain. It stands, it's a project that we've been doing here at NOAO along with the University of Arizona to try to essentially make sense of this jumbled data stream. And so the idea is that we'll take in alerts from LSST and ZTF and other sources at the top there, and we'll do a whole bunch of processing on them because the alerts from LSST are really just something went bump in the night, whoop, and you really get very little information beyond that. So if you want to characterize that source, if you want to add any information to it, if you want to make a prioritized list, that's entirely on us as the community. And so this is a multidisciplinary collaboration that has the computer science department across the road or across the campus, as well as the mathematics department now, and us here at NOAO, all trying to work together. And so it is a large team to do all of this. And the idea is that we'll characterize these alerts and give you a value-added data product. But it isn't an LSST data product, right? We're doing this mostly for funding, but not quite out of the goodness of our hearts. And hopefully it will still be a useful product for all of us in the community. And so the idea is that we'll try to winnow down that 10 million alerts per night into something that you can actually manage with the spectroscopy. And so all of these alerts will be archived. We'll have a database that you'll be able to query, much like gas jobs, for example, and get streams of. Hopefully we'll also have a more interactive sort of interface where you can write a little bit of code in sort of an IPython notebook, upload it into the NOIO data lab, and it'll run on alerts from LSST and give you some useful processing. And those alerts will go down to automatic brokers, as well as humans, investigators, and they'll hopefully feed back to us improved classification stuff. To make all of this work, it requires a giant infrastructure. You can't read this. It makes no sense. I've stuck an actual long version of it so you can stare at it later, but what we'll do during the notebook in the next half of this is step through this entire flowchart and essentially build toy versions of all of these. So what I will say here, though, is that every single box is some piece of Python code or C code. And so that's the stuff that we're writing. This outlined box around it is stuff that we are doing, and stuff that we aren't doing is outside the dashed box. And for the most part, the idea is that you winnow down the alerts so that red arrow becomes smaller and smaller as you go down, and hopefully find the most interesting things at the bottom. But you have to ingest them at the top. And once you've ingested them, we have to sort of add association and contextual information. So is there a galaxy near this source in LSST, for example? What's the history of this source? Is there a light curve? That's not something LSST's alerts are actually going to include. So it's entirely on us to store that history and reconnect these objects together to actually produce a light curve. And once we've done that, can we build an anatomy of the object? Can we characterize the object? Can we make some point estimates? What's the amplitude of this thing? What's its standard deviation? Is the light curve skewed in some way or the other? Once we have those sort of characteristics, we can compare those characteristics against a library that we'll build of known astrophysical objects. So a reference set or a training set. And we're calling that the touchstone. And after that, you can do your filtering, right? Because you can tell whether things are like things in the touchstone or not. And if they are, you can divert them because they're more or less boring. And if they stand out, then that's potentially really interesting. And that gives you the output at the end. So what I'll show you in video form and just talk through this is a run through of how the system works. And what we'll do is take some really weird alerts and put them in with a bunch of perfectly normal, boring things at the top of our flowchart over there, and just process them all the way through. And so this will actually combine more or less what you've seen. So like Cameron was talking about, to deal with this, we have to parallelize everything that we do. And so we have a cluster over here at NOIO, and it's got 6 big machines with a whole bunch of different worker nodes going underneath them. They're just basically the processors of that machine. And they start ingesting alerts and doing work on them. And the different stages that ANTARES runs are sort of labeled down here. So you can see where processing is taking place at any given time. So for the most part right now, things are going through feature derivation and then comparison with the touchstone and filtering. And every now and then, hopefully, most sources will get diverted because they're boring and not rare. But every now and then, something should get flagged. And it'll tell you, for example, why it's getting flagged. And give you some sort of a message. And this sort of message is written into a database, and that's the sort of thing that you would query on. Okay? This is all very nifty and it works pretty well. To make all of this work, to see how this will work, is what the bulk of this talk will be, and what the bulk of the hack session after this will be. So the notebook that we're giving you is essentially build a simple version of this. Okay? And hopefully we will do that in a way that reinforces pretty much all of the things that you've been learning in these last 3 LSST sessions. So this is boring, I'm done with that. So what was happening there and how is it actually happening? So when you start up ANTARES, we're going to get alerts from LSST. And so for parallel processing, we start up a bunch of master nodes that have a lot of fault tolerance with them. And those master nodes each start up a whole bunch of alert worker nodes. Now these things all monitor each other, so if one master node dies, it gets restarted by another thing, and the work that had been assigned to it goes to some other machine. And so this is an entirely large parallel architecture. And this is the sort of thing where you don't want astronomers trying to invent this. Go find a computer scientist and pay them well, because you'll simply do a really bad job of it. The next part of what we do is cross-matching and association. And so now we're starting to get into actual, forget the infrastructure, let's go to the science. And so when you want to cross-match, you have to look for external information against LSST alerts, right? And that's heterogeneous, right? There's different surveys in the sky, they are all different cadences, they all have very different properties. The LSST alert rate for us is way too high for web queries, so you can't sort of be using Astro Query, for example, to send out your favorite RA index across the web and get an answer a minute later. So what we're doing here at NIO is collecting a whole bunch of really large catalogs from big surveys, so things like SDSS, TUMAS, and NED locally. And we'll be cross-matching them using that hierarchical triangle mesh that we sort of talked about earlier, using SciSQL. So all of this is hopefully going to end up on LSST QServe, much like LSST itself. And this itself is a valuable data product, and we'll make it available through the data lab. And you'll hear a lot more about the data lab tomorrow, so I'm not actually going to focus on the cross-matching part, but I do want to give you a sense for how much stuff there is out there. So if we just take optical, IR, and high energy stuff, so gray, red, and blue here correspond to Chandra sources, TUMA sources, and SDSS sources. This is just a giant density plot across the sky. This is 190 million objects. And we're trying to search for a chunk of this from an LSST alert. But thankfully, there's some advantages here because we know where LSST will be pointing to take an image. And so we can preload the part of this database that we want into memory before we get the image from LSST and do our query against only a very small region of the sky. Okay? And that's a real advantage that we have. And these are, of course, static catalogs, but there's also time domain catalogs, and they've just been building up over the years. So this is a view of the time domain archive that we had in NOAO as of May of last year. And so you can see as cameras get bigger and bigger, suddenly the data rate is going to splurge. So DECAM is turned on now, and suddenly the southern sky is going to get splattered in blue and green here, showing you as a density map how many images there are at any given point. So this is really a visualization of what Moore's law has done in just a few years. Okay? And this will keep going, but essentially we now have a ton of contextual information, historically and time domain information, of the southern sky where LSST will be. But of course, the most valuable information is the information from LSST itself. And so you want to do feature derivation and characterization and try to tell people what that source is. And so you sort of see these kind of tables which are essentially point estimates, things like the mean, things like what the amplitude is, what was the RMS in the past, is it significantly different from another source that's nearby it, is it a galaxy, is it a star, does it have Fourier components? You guys have seen time series analysis in the first session, so hopefully that's familiar to you. Can we make sure we have the light curve? Is this a moving object, for example? So a lot of these things we'll get from LSST, a lot we'll be computing ourselves. And this is the sort of stuff that you'll be computing in that notebook. Once you have your features, you want to compare it against known objects, right? That's how you do your machine learning. You have to have a reference training set. And we are actually trying to characterize everything on the sky. So if you have to have a training set that's fairly comprehensive, then you have to have models for essentially everything on here. So variable stars, supernovae, pulsating stars, Cephiids of different kinds, all manner of things. And so we've been assembling a very large data set over here from different sources. And these are all heterogeneous. They're not ideal because they're not LSST. Most of them aren't, in fact, GRIZ light curves, because if you had GRIZ light curves in the time domain, why would you build LSST in the first place? So the bulk of the data is VNI. Most supernova data is, of course, type 1a supernovae, because that's what us horrible cosmologists go looking for. And some of the data is almost certainly mislabeled. Okay, these were looked at by human people, much like I looked through that Pan-STARRS web pages to give it a label. But we're also the same species that likes to see pictures of Jesus on toast. So we're not necessarily very good at this. And so there are entire classes of variability and transient behavior that are completely missing in this database that we have. But it is what we have to work with. So you have to start filtering things. Now you all know what Bayes' theorem is, yes? So let's assume that we have a new object from LSST. I have one observation. What do you think I can tell from that one observation about this thing? Using your intuition of Bayes' theorem, what would the likelihood function look like with one single point? Not very good, yeah? But the likelihood isn't the only part of Bayes' theorem. What's the other part of it?
Prior.
A prior. Brilliant. So a prior here can actually still give you some information even when you have a single point on light curve. So Kepler, as you all know, has been staring at one small chunk of the sky, and it has a really, really good empirical model for what variability is in that one chunk of the sky. So 155,000 stars, but it covers an entire range of spectral types, right? And the light curves from Kepler are exquisite, so we really have a very good sense of what the distribution of variability from Kepler is. And because it's one chunk of the sky, there's a certain stellar population in that one region of the sky, but I can change that stellar population to any other background stellar population if I had a model of the galaxy, which I do. It's called the Besançon model. And so you can essentially take one underlying stellar population and rescale your histograms to another part of the sky, and this is what we do. And so here is a prior, okay? Most things don't vary. Giant big peak at 0. And some things have strong negative variations, they get brighter, and some things have positive variations. And so if I had a prior like this and I had an excursion from the background of, say, a magnitude, I could decide how rare that is and decide whether that was worth following up. So I could simply set a threshold here of, I would like 1 in a million things to be rare, and that gives me a magnitude cutoff as to where it should be. So a prior is still a really useful piece of information, but of course you want to be able to extend this as you get more and more observations. And remember, when you have just 2 or 3 points in a light curve, you still have to be able to make a decision fairly quickly, but it's really hard to do with very little data. So this is essentially the entire framework that you can use initially, because you can't even compute something like a standard deviation with 1 point. And so what we can do is take all of the light curves that we have in our touchstone and calculate what we call the structure function, if you folks know AGN stuff, right? Essentially take any 2 points on the light curve and calculate what the difference is. And any new alert from LSST is somewhere in that space. And so you have now again a prior, but now in 2 dimensions to try to classify things. And so what that actually looks like is this. So on the x-axis here is a difference in time, delta t, and how much the magnitude changes is on the y-axis, delta m, for 4 different, the LSST passbands, G, R, I, and Z. And so you can plot out what supernovae, for example, do in this space. And what you quickly see is that as you get to larger and larger separations, you can actually tell the difference between type 1 and type 2 supernovae pretty quickly. So something like a week of observations of LSST starts to give you a little bit of constraining power. It's not a whole lot, but as you have 4 colors, you can do a little bit better and better. And you can also do this for variable stars. That's what this sort of thing looks like. And you can actually tell pretty much straight from inspection that different variable stars do in fact have very different behaviors over different time scales. And so even without a period being computed, even with just a few points in the light curve, you have prior information because you already know what the background of variable stars looks like. You have some idea what light curve shape is, so you can make some kind of a classification. Of course, this isn't ideal, and so you want to be able to do better than this. And so you can start to, as you get more and more points, calculate those sort of point estimates that I talked about earlier, things like the standard deviation, things like kurtosis and skewness. And then you can do something like principal component analysis, which is a technique that you've hopefully all seen again in this LSST-DA session. Right? It takes, it's just an orthogonal linear transformation, moving it into a basis that just best explains the variance. And so, for example, the V1 axis here is most of the job of explaining the variance, and then V2 is constrained to be orthogonal to V1 and explains what's left in that data in this 2-dimensional space. This is great because it's really well documented, it's really easy to use. You can reduce a large feature space down to a few numbers, and so you can prevent overfitting. And let's show you how this actually looks. So assume I have just a few points on a light curve. I've gone and done my PCA, and I have some space where I've color-coded different points in 2-dimensional PCA space by class. So I can see the light curve, the raw light curve that I have over here, and I can see what it looks like when it's folded, and I can compute features on this thing and run PCA on all of that. And as I move through this space, I can actually see very quickly that things look very different. So if you look at those phase curves on the top right-hand corner there, these are the RL array, and they look very, very different from the stuff down here, which are like eclipsing binaries. And you can actually see that even in these 2 dimensions, they separate out pretty nicely. So these are RR type ABs, and eclipsing binaries are down here. Contact binaries are also down there because they look very similar to RL array. And things are in different parts of a parameter space, but we can essentially, for a whole bunch of different classes of objects, even with just two dimensions in PCA space, start to tell the difference. And of course, there's a whole bunch of contextual information that we have and we can associate with. So if I, for example, click on one of these points, like, maybe I have to unselect the thing first. There you go. So compare this with the web page that I showed you earlier, where for Panstars I just gave you a bunch of links to go follow this stuff up. Here it's directly available because we queried it from our local database. On the fly, whole bunch of things like the dust properties in the region, what is SDSS information is, what the colors are, all things like Sinbad cross matches, things that I can use to really tell what this object is very, very, very quickly. So once you've gotten some metric in this 2-dimensional space or n-dimensional space to classify objects, you can start to decide whether the object is rare or not. And so you can throw it at something like k-nearest neighbor, which is again an algorithm hopefully you've seen in these LSST data sessions, right? And if the object looks like something that's in your reference touchstone, then all of those classes of objects that are colored by green end up near the origin. The distance to that class is very minimal. Whereas if it really is an outlier, then it isn't in this normalized distance space near anything at all in your reference library. It is really an outlier. And so we did this. It turns out that you can get sort of like 90% accuracy with just a single passband for variable stars, and that's not bad at all. But the question is, can we do better and better than this? So this was very coarse characterization, used things like the amplitude, the skewness, and the kurtosis. And so that's the sort of numbers that you should expect from the notebook that you'll be working on after this, is something around the 90% level, because that's about what those features have. We in fact aren't giving you a period in that notebook, so you'll do a little bit worse, but that's okay. We want to characterize things as we get more and more observations, so you can start doing time series analysis. So you all learned about Lom's-Cargill and things like phase dispersion minimization and conditional entropy, which Mark Graham actually wrote a great paper about that I keep on my table because it's wonderful. And we're trying to generalize that to work with multiple passbands. Good stuff. So we can model this as we get more and more data with more and more sophisticated techniques. So you all heard about Gaussian process regression, right? And wavelet decomposition. It was very brief, presumably, from that first session, but we'll actually see it again today. So a Gaussian process is great because it's a completely non-parametric way to describe light curve shape. And this thing works for variable stars, it works for supernovae, and I haven't asserted there's a single functional form for either of these things. I've simply been able to describe the shape of the objects by simply asserting that there's a correlation between the points in light curve. And so it's completely non-parametric. It gives you a very robust outlier, resilient way of classifying data. And now you have a really nice, smooth model of the shape. And this is nice because most machine learning algorithms want you to have evenly sampled data with no gaps at all, with no outliers at all. And there was no good way to make that with astronomical data normally. But you've essentially figured out a way to build that with this really nifty interpolation to it, essentially. So once you have these shapes, you want to reduce the complicated Gaussian processes down to just a few numbers. To do that, we can use a thing called wavelet decomposition. So if you have a nasty shape like that sawtooth curve, you can throw it at a wavelet decomposition, in this case using just square functions, and start to describe them. And so as you add more and more of these scaling functions and square functions, you can do a better and better job of describing the shape of these things. So this is using what's called a Haar wavelet. It's just a step function, but the essential idea is that even though it's a completely discontinuous step function, it does a really pretty decent job of mimicking the shape of that curve with just 6 numbers, okay? That ain't a bad thing. So you might hope that this works for supernovae. It does work for supernovae. This is a plot that my undergrad made. He defended his thesis on doing just this a couple of weeks ago. So that's a type 1a supernova light curve. It's upside down because the plotting package is useless. And this is how you break it up into a bunch of wavelets. So you can decompose this thing into these unbalanced Haar wavelets with some coefficients that essentially describe the entire shape of that curvy light curve. And once you've done that, you can toss all of this away and simply focus on that one vector of numbers, okay? The coefficients. That describes everything that you need for the shape. That is perfectly good for classification, right? That's your feature vector. And you can do this on your training set. So you have your training set having a whole bunch of shape numbers. And you can do this on your new data, and you're simply comparing numbers. That's not a hard thing. So this is, again, the PCA decomposition that I showed you in that interactive web page. Different color coding, but otherwise the same data. If we change the feature set around, we can do a much better job of separating these things out. So this is using a t-distributed stochastic nearest neighbor embedding, a t-SNE, which is a visualization tool that you folks saw. And simply flipping back and forth, you can see again for the variable stars, with adding more data and getting a better light curve, I've suddenly been able to do a much better job of classification and separating these different groups out. And this was for variable stars. This also works for type 1a or different kinds of supernovae. So you can see the type 1a supernovae sort of live over here, whereas type 2s are pretty well separated out over there. And the 1bc's, which are really kind of like type 1a's, are sort of thrown in between. Superluminous supernovae for Simon fall nicely on an edge here. So they're actually really easy defined. And once you have these nice wavelet features, and you have these vectors for the touchstone and your new data, you might say, oh, well, I want to classify these things and actually put a label to the objects that I don't know from LSST. And so you have a machine learning algorithm, right? This is the stuff that you've again been seeing. And so we use a random forest, for example, to do this. So a random forest is just all machine learning algorithms are ultimately just a mapping from those input features to an output feature. And a decision tree is the simplest way to do that, right? A decision tree is an if statement. If something, then this, otherwise something else. There is really nothing more complicated to a decision tree. But if you take a whole bunch of those decision trees and put them all together and build a forest of those things, and very cleverly decide how those splits happen, then you build this thing called a random forest. And a random forest has just a bunch of those if statements, and so your vectors go in at the top, and they get classified and split on different trees at different points. At the end of each tree gives it a label, and then you just do voting, so k-nearest neighbor kind of voting, and say the majority rules, and that's the final class of the object. So this works again. It's simple, it's robust, it's also only as good as your feature selection, so you have to really be a little bit careful at this point, because as you've gotten more and more complicated features, you can also build in more and more complicated biases that are hard to find. And so if you start to see your classification accuracy dropping for one particular class, now you have to worry. And so you'd like to, of course, have a metric then to measure how successful your entire pipeline has been. And so you've seen this before as well. These are receiver operating characteristic curves. And they really just measure how well you're doing as a function of the true positive rate and the false positive rate. And in an ideal universe, you maximize the true positive rate and minimize the false positive rate. So that would be up here, right? So a perfect classifier would have an L, and it would have an area under the curve of 1. Of course, no classifier is perfect, and so they end up forming some kind of curve in that space, and you can measure how well they do for different classes at different thresholds. And if you were just random guessing, then you would have a diagonal line. So you're going to be somewhere between those two things. But this is really useful if you, for example, care about type 1a supernovae, because you can decide where you want to be in that space. For example, making a photometric sample of these things.
I have a question.
Yeah.
So this, maybe you're talking about this, but I mean the RC for multiple classes, is a bit more difficult because
Absolutely.
you want to either do one against like
Yeah.
all of the others, or it becomes very ambiguous what the result is. Right?
So what I like to do is build up a matrix there for each class along one axis and see
The
how much the
confusion
confusion
matrix.
matrix exactly, and see how much contamination there is from one class in all the other classes.
Mm-hmm.
There's no one single metric that you have to use. Okay, with all of these things, when you're doing machine learning, there isn't one nice way to go from top to bottom. People like to treat them like black boxes, throw some data in it, it works, it gives you answers out. But there is a human aspect of these things, all of these algorithms. The human aspect is deciding what features matter, what you have to compute in the first place, how do you minimize bias, and ultimately you have to worry about your data. That's why you're a scientist. So these ROC curves for supernovae I'm showing here, we've done this on simulated data and real data. The simulated data was done by Michelle Lochner and just this sort of stuff last year, and she got really high classification accuracies, and I was like, wow, we should totally try to see how this works on real data. And 98% classification accuracy is wonderful, right? And then you take real data and it doesn't look nearly as good. But it ain't bad. It's actually still like 94%. That's okay. Because if I want a type 1a supernovae sample that's photometrically selected, I could say I want a really low false positive rate. So I could take something like less than 0.1 and simply say, well, I'm going to lose a lot of my sample, but my sample will be really, really pure and really, really free of contaminants and really good, hopefully, for cosmology. And so there is also the stuff that doesn't fit with anything that you've seen so far.
But sorry, can you ask a question on that?
Yeah.
What does OSC stand for?
The Open Supernova Catalog is a database run by James Gautham. So
Sorry, you should finish. I know what that means, but
yes.
I don't know that everyone
So OSC is essentially every real light curve of a supernovae ever. That's public.
Published.
That's published in public. And so we simply threw it at that entire classifier. We used a few different wavelet schemes to match what Michelle did. And it works out pretty well that you can actually solve this problem with pretty good accuracy with supernovae, and you actually do significantly better for this with variable stars we've learned. Mostly because variable stars don't go away, they just stay there and keep flopping on and off. So they're much easier to study. So the output from all of this thing, hopefully, is this notebook that you'll be building in the next half of this session, and will hopefully reinforce all of the stuff that you do. So you have about an hour and a half now to go build this entire monstrosity that I've talked about. Hi.
Can I ask a question about
Please.
the wavelets?
Yeah.
So the wavelet analysis you did, was that on regularly sampled time series?
Yeah, so I used the Gaussian process to essentially interpolate
okay.
light curves onto a regularly sampled grid.
And you're assuming for your covariance matrix in the Gaussian process just squared exponential?
No, we actually moved to Matern 5.2 plus white noise.
Okay.
Technical detail and stuff.
Yeah. No, that all makes sense.
Yeah.
Okay. Good.
Hi.
If you're deciding how to allocate follow-up resources, I guess how do you decide to either prioritize the precision or the recall? Like, how do you make that cost analysis?
Great. So there's no single answer to this question, and I think ultimately the choice is left to the astronomer as to what they want to go follow up, right? If you have a telescope proposal that's been accepted, let's say MMT or Magellan, and you're the PI, well, you get to decide what you follow. What we're going to do is give you a annotated list of all of these alerts with a whole bunch of features to help make that decision. And we can pick objects that are rare and don't look like anything we've seen before and say, here is using some set of rules that we came up with that we think most of the community agree on, a rank system. And you can completely ignore that if you choose to, okay? My hope is that that ranking system is the sort of thing that will, instead of going to a human, go to an automated telescope. So what I would like is to have an LSST alert hit ANTARES, get classified in 37 seconds. An alert is reissued from ANTARES, goes to some telescope like say Las Cumbres or the SED machine at Caltech, and it's sluiced to the right place, takes a spectrum, and we close this loop within a few minutes. Completely automated, no human at all. that would be why I think you have to have a ranking system. But you should make your own decisions. This is why they pay you the medium-sized bucks.
Are there any, oh, yes, Eve?
How are you going to incorporate LIGO signals into this?
So the way the LIGO filter that we have currently works is we load in the entire banana from LIGO and essentially look for every single source in that banana that's been significant, and then come up with very simple if statement rules to see whether these are potential counterparts, because we know something about the counterparts. We know there's not going to be a variable star, for example. So there's no reason to take, we see something that looks like a transient, is a transient in a nearby galaxy. Do we have an edge? That's a really good giveaway, hopefully, for something like LIGO. Because we know that the sort of things that we'll be seeing are relatively low redshift, especially the things like supernovae that are exploding. Black holes and stuff we won't see anyway, so I'm not worried about that.
Any further questions for Gautham? Okay.
What's the web interface you are using for the PCA?
For the PCA stuff?
Yeah.
We made it ourselves in-house. It's mostly JavaScript and D3.